the limit comparison test. Here's the idea. If you remember for the direct comparison test, I had a very first example was 1 over 2n minus 3, right? We showed that that was greater than 1 over 2n. This diverged, so the bigger guy had to diverge. Now, here's another one, looks very similar, only the sign is different. But here we immediately run into a problem. You would expect that this series is going to diverge, because when n gets really big, it doesn't matter if you're doing 2n minus 3 or 2n plus 3, it's going to behave the same way. And in fact, that's true. This one does diverge. But what happens if we try to do the direct comparison test? I'm out of luck, because 2n plus 3 is bigger than 2n. So 1 over 2n plus 3 is less than 1 over 2n. And my direct comparison is a failure. It gives no information because the sign is wrong. Not the sign is wrong, the inequality is the wrong way, right? Something that's smaller than something that's diverging could diverge, could converge. The test is inconclusive. And let me point this out. This is the first time we've seen this. Oh, the test is inconclusive. But we'll see that a lot. One of the things about all these tests, as we go through and learn more of them, there are cases when they are inconclusive, and that means that I can't use this test, I have to use another one. Okay? So, therefore, if I wanted to do this, again, I could also do this with integral testing. But if I wanted to do this, I can't do it with a direct comparison, but still there must be a way, because we know that when it's very large, this thing doesn't matter. And there is a way. That way is the limit comparison test. Okay? So for our limit comparison test, what we need is to look at the limit of not whether an is bigger than bn or an is less than bn, but what is going on in the limit as n goes to infinity. And we're going to look at the ratio of those two series. So I'm going to take my two series. Again, these are series with positive terms. And what I'm going to do is I'm going to take the limit as n goes to infinity of the ratio, an over bn. And it doesn't matter which one is an or bn, just whatever they are. And as long as that ratio is a finite number that's not a zero, so c is greater than 0, and c is not infinity, then both series behave the same way. So it's okay, by the way, for c to be 1. It often is. Unlike other tests when it's bad when you take the limit and you get to 1. Here, what's bad is if you get 0 or infinity. Okay? So, for the example that we had, which I lost which one it was. What was it? 2n plus 3? We can do very easily. We're going to compare it. Limit compare. I'm just going to write use limit comparison with 1 over 2n. Okay? So I'm just going to take the limit as n goes to infinity. And out of space here. I hope you guys can see this. If it gets too small, I did that one over that one. Now I can make it a little bit bigger. This is 2n over 2n plus 3. Okay, well clearly as n goes to infinity, this goes to 1. Okay? So what does that tell me? It means both series behave the same way. So, and I know this one diverges, so that tells me that this one also diverges. Diverges. Okay. So this is most useful, these tests, both times, but they're most useful with rational functions or algebraic functions, and with that like 2 to the r to the n kind of business. Okay. So let me do a couple more examples here. I'm going to have to erase this, but remember what we're doing. I'm just going to put it up here. We're going to take the limit of an over bn, and we want this to be some finite. Okay, what does it mean if you do get 0 or infinity? It means you compared your series to the wrong series, and you should try it again to compare it with a different one. Okay, I'll give you an example in a minute. So, something that's somewhat complicated or a little bit more complicated, I don't want to mess around with, is this bigger or smaller or whatever, a bunch of inequalities. I mean, I like inequalities, but, you know. So for me, the limit comparison test is just a much simpler way to go. But what do you want to compare it to? The best thing to do is to look at the highest terms on the top and the bottom, especially because you're going to be doing this for typically a rational function. So I'm going to look at the highest order terms. And you can just pick them. n squared over 3n to the 4th, right? Just ignore that other stuff, plus 1, minus 1, whatever. Okay, so if I simplify that, this is really 1 over 3n squared, right? N's cancel out. So I'm going to compare it to 1 over 3n squared. I know the series then will converge. 1 over 3n squared is going to be a p series that's convergent. So what we're going to do is that we're going to compare to this guy. And you can even write it here, p greater than 1. Right? We know it's a convergent series. Okay, so now if I do my limit, I'm going to do an over bn, it doesn't matter which one it is. This guy over this guy. Okay? Let me write this properly. I'm going to get 3n squared times n squared minus 1, and then 3n to the 4th plus 1 in the bottom. So this is going to be 3n to the 4th minus 3n squared. And on the top and in the bottom I have 3 n to the 4th plus 1. Well, we can see that's going to go to 1, right? Because it's going to go to 3 over 3. But we should probably do enough work to show that properly. So I'm going to multiply top and bottom by 1 over n to the 4th, like usual. So this is going to be the limit as n goes to infinity. And this will give me 3 minus 3 over n squared over 3 plus 1 over n to the 4th. These guys go to 0. I end up with 3 over 3, which is 1. Okay? So what that tells me, again, is that these two do the same thing. So, since this guy converges, this one also converges. Well, I don't really have space. If I had space, I would write, so this guy is a convergent series. So, convergent. So when you get that number there, again, it's going to depend on what you compare it to. I could also have forgotten about the 3 and just compared it to 1 over n squared, which I know converges. I would end up with a different number. What would I end up with? 1/3. I could end up with 1/3. That's okay. The fact that what the actual number is not that important. Just that it's a finite number, so it's not infinity and it's not 0. That's the important part. Okay, let me do another one. So this is actually a cube root. Cube root of n to the 7th plus n squared. All right. So we can proceed in the same sort of way. What are we going to compare it to? We're going to compare it to the highest terms. But when you got like a square root or a cube root, some kind of root business, you have to take that into account, right? So my highest terms on the top I have an n, and on the bottom I have an n squared with a 1/3, right? So this is going to be n to the 7/3. Let me write that a little bit big so you can see it. Right? Okay. So really, this is n to the 1, which would be 3/3. So this would be 1 over n to the 4/3. All right, well, 4/3 is bigger than 1. So this guy's going to converge. And the series is going to converge. So this one converges. So if we do our comparison test right, then this guy's going to converge as well. And then it's very similar to the previous example. So really, the difference here is just that we have to remember to do this thing with really taking the highest order term to be the actual highest order term. Just kind of have to be aware of that. So this is going to be n to the 4/3 times n plus 5. And then in the bottom, I'm going to have cube root of n to the 7th plus n squared. All right, so rewriting this, a little bit more space. Rewriting this, up here, I'm going to have n to the 7/3 plus n to the 4/3 divided by this thing. Now, I can't technically break this up, of course, right, because the square root or the cube root, although it doesn't distribute that way. But I can still do the same thing. You can see I do have the same thing on top and bottom here. Okay? And then when I multiply there, I'm going to have limit as n goes to infinity of 1 plus, all right, what is that? 1 over n, right? 4 minus 7. And then this would be cube root of 1 plus 1 over n to the 5th, right? Because once I took that over, I have n squared divided by n to the 7th, so I have n to the 5th. Both of these go to 0, and I'm left with a 1. Okay? So, this guy converges because p is greater than 1. So, by limit comparison, our series also converges. Okay, so I want to talk a little, I know this is getting a little long, we're almost at 20 minutes, but I want to point out what would happen if I picked the highest order terms wrong, okay? So if I forgot about this cube root, which is a fairly common mistake, and you just did it like this, okay? This is, of course, still a convergent series, but look what's going to happen to this limit. This is going to be n to the 6th here. And so I'm going to have n to the 7th plus 5n to the 6th on the top. And then I'm going to have this cube root here. Okay? And so if I divide by top and bottom by n to the 7th, what am I going to get? In the top I have 1 plus 5 over n. And the bottom, okay, I'm going to take that into here. Then I'm going to have to do, I'll write it out. N to the 7th over n to the 21, right? Because I no longer have the 7 over 3, or the 4 over 3, whatever it was before. And then this would be n squared over n 21. Okay, so you can see that as n goes to infinity, this is going to go to 0, and that's going to go to 0. So let me write it out a little bit better here. Out of space. So I've got 1 plus 5 over n, and then this would be cube root of 1 over, what the heck, is this 14, right? 1 over n, sorry, I'm out of space. That is a problem with the smaller board. 19, right? So this goes to 0, this goes to 0, and this goes to 0. So this is 1 over 0. Well, I don't want to write that on the board, but this whole thing is going to go to infinity. Okay? And if it happened, I had these switched, my limit would have gone to 0, right? So this is telling you that you did it wrong. You compared to the wrong thing. Because if you're doing comparison test, for comparison test to give you any information, this C has to be something that's not 0 or not infinity. So this was wrong.